Welcome back to the deep dive. Today we are looking at a topic that, usually gets pigeonholed as just developer tooling.
hmm
But if you look closer, it's actually a fundamental shift in the architecture of the internet. It's a change in how computers speak to one another.
It really is. We're moving away from the old standard of just like listing resources on a server
Right.
to a model where we actually think in graphs.
And thinking in graphs sounds a bit abstract, maybe a bit academic.
It can, yeah.
But the practical application here is massive. We are talking about the evolution from resource-oriented APIs to intent-oriented APIs.
That distinction, intent versus resource, is everything.
Yeah.
The technology we're analyzing to explain this shift is GraphQL.
Right. And I want to set the stage immediately here because I think a lot of people hear GraphQL and they just assume it's a database thing.
Oh, that's a common misconception, like SQL.
Yeah.
But it's not a database. It's a query language for your API and, crucially, a server-side runtime for executing those queries. It sits in front of your database.
So it's a translator.
In a way, yes. It's a layer that lets you define a type system for your data, and then it executes queries against that system.
Okay, let's back up a bit. Because to understand why this shift is happening, we have to look at the environment that spawned it. We need to go back to, 2012?
The year of the mobile pivot, yeah.
Exactly. Before this, we were in the desktop era. If you were building a web application, you just assumed your user was on a hardwired Ethernet connection or at least solid Wi-Fi.
Infinite power plugged into the wall, a massive screen.
And in that environment, engineers got a bit lazy with efficiency.
Totally. If you downloaded a massive file just to display a user's name, nobody really noticed. Bandwidth was cheap and fast.
Then the smartphone just explodes onto the scene. Suddenly you have millions of people accessing complex applications over 3G networks.
And 3G was rough. I mean, high latency, dropped packets.
And battery drain.
Oh, the battery drain. Every time you turn on the radio and a phone to fetch data, you are burning battery.
This is where Facebook hits a wall. They're trying to build their newsfeed for mobile. And the newsfeed is a beast.
It is. I mean, think about the data structure. It's not a flat list. It's hierarchical. You have a feed, which has stories. Stories have authors. Stories have comments.
Comments have authors. Authors have profile pictures. It's this deep nested tree.
Or graph. And they were trying to load this using the industry standard at the time, which was REST.
And REST was failing them.
Miserably.
Let's break down why. We often use the fixed menu analogy for REST.
It works because REST is resource-based. You have specific endpoints URLs that represent resources, like users or posts. These are items on the menu.
And if you hit the user's 123 endpoint, the server decides what's on the plate, not me.
Precisely.
Yeah.
The server dictates the data structure. So say you're Facebook. You want to render a list of post titles on a mobile screen. That's it, just the titles.
But the post's endpoint is hard-coded to return the title, the body, the timestamp, the author ID.
All the extra metadata.
I ordered a side salad, and they brought me the entire buffet.
That's overfetching. You're downloading kilobytes of data that the user will never see. On a desktop, fine. On a flaky mobile connection, you're clogging the pipe and wasting the user's data plan.
But I feel like the opposite problem is even worse.
Underfetching.
Yeah, the scenario where the menu item isn't enough.
This is the latency killer. It's often called the N+1 problem.
Okay, walk us through that.
Okay, so you want to load the news feed. You hit feed. You get a list of 10 post IDs. Great. But now you need the author's name for each of those posts.
And the feed endpoint didn't give you that?
Nope. So you have to go back to the server.
For each one?
You have to make a separate request for each post to get the author details. That's one request for the list, plus 10 more for the details. 11 round trips.
And on a high latency network, that handshake time just adds up. You're looking at a spinner for 4 seconds.
Exactly. And this also stems from tight coupling. The client application is totally bound to the server's rigid decisions about how data should be grouped.
So if the product team wants to change the UI, they have to go beg the backend team to create a whole new endpoint.
Right. So Facebook says, enough. They need a way to decouple this. They want to shift from imperative, go get this, then go get that, to declarative.
The chef's table approach.
Yes. Instead of a fixed menu, you have a conversation with the chef. You tell them exactly what ingredients you want on the plate.
I want the user's name and the titles of their last 3 posts, and nothing else.
And the server returns a JSON object with exactly that. No waste, no multiple trips, one request, one response.
It sounds so obvious in hindsight, but that shift to a single endpoint architecture is radical. In REST, you might have hundreds of URL
In
endpoints.
GraphQL, you usually just have one.
That's why.
And that one endpoint acts as a gateway.
Let's get under the hood, though, because ask for what you need is a nice slogan, but how does it actually work?
It relies on a strict schema. This is the contract. Before you can ask for anything, the developers define a schema that maps out every available type of data and how they relate.
So the schema says we have a type called user, and users have a field called name.
Correct. But here's the magic piece that I think gets overlooked. The resolver.
The worker bee.
Pretty much. The resolver is a function. For every single field in your schema, there is a corresponding function whose only job is to go fetch that specific piece of data.
And this is where it gets cool for system architecture. The resolver doesn't care where the data comes from, does it?
Not at all. And this is the superpower. You can have a resolver for a username that queries a PostgreSQL database.
Okay.
And in the same request, you can have a resolver for latest shipment that hits a legacy REST API and another for current temperature that hits a third-party weather service.
So the GraphQL runtime sits in the middle. It takes my request, dispatches all these little resolver minions to go to different systems, gathers their answers, and then stitches it all into one clean response.
That is exactly what it does. It's an orchestration layer. It masks the complexity of your backend mess. And let's be honest, most backends are a mess.
Hides it all behind one clean interface. That's the backend for fronting pattern, isn't it?
Perfectly suited for it, yes. It acts as the glue.
I want to touch on the developer experience. We mentioned schema first versus code first. Is that just a preference?
It changes the workflow. Schema first is fantastic for large organizations. The front-end and back-end teams agree on the schema, the contract, before a line of code is written.
So they can work in parallel.
Exactly. The front-end can mock the data. The back-end can build the resolvers. No more blocking each other. It speeds up iteration cycles significantly.
Let's look at the data itself. One thing that clicked for me was the mirror effect.
It is very intuitive. The shape of the request literally matches the shape of the response.
So if I write a query that looks like a JSON object with empty values, query username, I get that JSON object filled in else. You never have to guess. It's deterministic. If you didn't ask for it, it won't be there.
That handles reading data, the queries. But what about changing data, writing? We call those mutations. And again, the efficiency story holds up. In a REST world, if you wanted to do a complex operation, say, create a project, add a user, then send an email, that's 3 separate API calls.
Create, wait for success, update, wait for success, trigger email, lots of waiting.
In GraphQL, you can batch these. You send one request saying do A, then B, then C. The server executes them sequentially and returns the result for all 3 in one go.
It really feels like this whole thing was designed to baby the network connection.
It was. It assumes the network is the bottleneck, so it optimizes everything to minimize chatter.
Okay, so developers love it. It's efficient, it's clean, but my skepticism radar is pinging here.
Uh-oh.
When you give a client that much power to ask for exactly what they want, aren't you opening a massive door for abuse?
You absolutely are. Security in GraphQL is fundamentally different from REST.
In REST, I just secure the endpoint. I put a lock on the door to administrators.
Right. But in GraphQL, you have one door, GraphQL, and everyone comes through it. You can't just lock the door. You have to inspect what they're asking for.
The attack surface shifts from the endpoint to the schema.
That's the key.
So what's the nightmare scenario?
Recursive queries. The malicious librarian scenario.
Explain that.
Imagine you have a schema where users have friends, and friends are also users.
Standard social network
A
stuff.
hacker can send a query asking for Alice's friends and her friends' friends and their friends' friends and just nest it hundreds of levels deep.
Oh, wow. User friends.
User friends,
Yes.
exactly. Even if the database is small, the server attempts to resolve this exponential tree. It consumes all the CPU and memory trying to build the response, and the server just crashes.
A denial of service attack.
But you don't need a botnet. You just need one complex query.
That is terrifying. One text file brings down the API, so how do you stop it?
You need guardrails.
Yeah.
The most basic one is depth limiting. You just configure the server to say, if a query is nested more than, say, 3 levels deep, reject it immediately.
Simple enough.
It's very effective. For more sophisticated setups, you use complexity analysis. You assign points to expensive fields. Maybe fetching a name costs 1 point, but fetching a friends list costs 10.
And you give every request a budget.
A budget of, say, 1,000 points.
Yeah.
If the query costs then doesn't one, the server drops it before it even tries to execute.
There's also that feature, introspection. We pitched it as a pro for developers, but isn't that a huge con for security?
A huge con if you leave it on in production.
Yeah.
If introspection is enabled, a hacker can just ask the API, tell me your entire schema, tell me every field, every type, every relationship.
You're handing them the blueprints to your bank vault.
That's the perfect analogy.
Yeah.
So rule number 1, disable introspection in production.
Without a doubt.
Without a doubt.
Okay, let's move to the trade-offs. We've hyped the efficiency, but I know for a fact that transitioning to GraphQL can be painful. What breaks?
The biggest shock for seasoned engineers is caching, because the web runs on HTTP caching. CDNs, browsers, they're all really good at caching GATE requests. If I request logo.png, the CDN remembers it. The next person gets it instantly.
But in GraphQL.
Everything is a POC request to GraphQL. The URL never changes. The CDN sees a request to GraphQL and another request to GraphQ. It has no idea. One is for a user and the other is for a product.
So you lose all that free caching infrastructure.
You break the internet's native acceleration. You can fix it, but it requires work. It's not out of the box.
What about on the server side? You mentioned the N+1 problem earlier as something GraphQL solves for the network, but doesn't it just create a new version of it for the database?
Sharp catch, yes. If you write your resolvers naively, you create a database disaster. Say you ask for a list of 50 users and their profile pictures. The runtime calls the user resolver once you get the list.
Okay.
Then for each of those 50 users, it calls the picture resolver.
So the database gets hit 51 times?
51 SQL queries for one incoming request. Your database administrator will scream at you.
So how do you fix that?
You use a utility called a data loader. It's a batching tool. It waits a few milliseconds, collects all 50 of those requests for pictures, and sends one query to the database. Give me pictures for these 50 IDs.
Okay. So it's solvable, but it's an extra layer of complexity you don't have in a simple REST endpoint.
Exactly. And that leads to the last big trade-off, error handling. In REST, status codes mean something. 404 is not found. 500 is server error.
Sure.
In GraphQL, if the request hits the server successfully, you usually get a 200 OK status, even if the data fetch failed inside.
So I get a 200 OK, but inside the JSON it says error, database on fire.
Precisely. This breaks a lot of monitoring tools that just scan for non-200 codes. You have to actually parse the body to know if something went wrong.
This sounds like a significant decision matrix. It's not just GraphQL is better, it's GraphQL is different. So help the listener decide, when do I use it?
Use GraphQL if your data is highly relational. If it's a graph like social media, e-commerce with related products, complex dashboards, it shines.
Or if bandwidth is the main constraint.
Yes. Mobile apps, IoT devices, smartwatches, anywhere you need to minimize the payload size. It's also the go-to choice if you need that facade layer to stitch together a bunch of microservices.
And when do I run away from it? When should I just stick to REST?
Stick to REST if you have simple, flat data. If you're building a blog, a simple to-do list, an internal admin tool where efficiency doesn't matter as much as just getting it done, don't over-engineer it.
Or if you rely heavily on caching.
If your site is content-heavy and static, like a news site where everyone sees the same article, REST and a CDN are going to be much simpler and faster.
And what about binary data, like files?
Great point. GraphQL is text-based. It handles JSON. If you are uploading massive video files or images, do not pipe that through your GraphQL resolvers. Stick to a standard REST endpoint for that.
It seems like the industry has really settled into a hybrid model.
Most mature companies use both. They use GraphQL for the complex user-facing client apps and REST for simple services or file transfers. It's not one or the other.
As we wrap this up, I want to zoom out to the so what for the future. We talked about intent-oriented APIs.
Right.
And I've been thinking about the rise of AI agents, LLMs. We are moving toward a web where the user might not be a human tapping a screen, but an AI agent trying to accomplish a task.
That's a fascinating frontier.
Think about it. If an AI agent wants to book a flight and a hotel, does it want to guess its way through 20 different REST endpoints, parsing useless data to find the one ID it needs?
No, that's inefficient and error-prone for an agent.
But with GraphQL, the agent can introspect the schema, it can read the instruction manual and then construct a single precise query. I need flight to London under $600 and hotels in Soho.
The declarative nature of GraphQL matches the declarative nature of AI prompts. The AI states its intent, the API fulfills it.
It feels like GraphQL might actually be the native language of the AI-to-machine future.
It's very possible. When the client is smart enough to know exactly what it wants, you want an API that's designed to listen.
Something to think about next time you're scrolling through your feed, wondering how all that data got there so fast. That's it for this deep dive into intent-oriented APIs. Thanks for listening.